In this movie, we are going to look at easing by curve. And what do I mean by that? Well, I'm going to remind you of things from high school. We're going to look at graphing. We really need to talk about this a bit just to get an idea or just a reminder of what graphing is all about. Well, one, because in order to be an informed citizen, you really need to know about graphs. And also, to be a graphic designer, that's probably important as well. Because, if you do go into some kind of education or something, or even media, you're going to be dealing with graphic information. And it's important to understand what at least this type of graph that we're going to talk about tonight means and how it works. So if this is actually old knowledge for you, I apologize, it might be boring. If it's review, it's good. If it's new stuff, wow, where were your high school teachers at? Okay, so we're going to start off by looking at a coordinate system. This is basically just a grid, and it's got two axes and a bunch of squares. Okay. The horizontal, or actually I should start off with talking about the very corner of our grid, which is the 0, 0 point. And this we also call the origin. So that's this thing right down in the lower left corner. And everything is numbered and measured from this point. Okay. We then have the x-axis, and this is the horizontal axis that increases as we go to the right. Going up and down, we have the y-axis. This is the vertical axis, and it increases as we go up from the origin. Now, why is this different from what we've all learned about the coordinate system in Flash? This is actually just the opposite as far as the y is concerned, right? The y in Flash gets bigger as we go down. Why is it this confusing? Why couldn't they just make it the same? Any ideas? Well, we do have somebody to blame it on. I'm actually fairly certain this is the guy to blame it on, but I'm not quite positive. It's this guy right here. Seems like the kind of guy that we could blame something like this on. Look at that forehead. Look at that hair. This is Philo T. Farnsworth. And Philo T. Farnsworth actually was the first person to make an all-electronic television camera and television transmitting system. He did this in the 20s, and he was only like 21 years old when he did it. He actually, according to Wikipedia, had the idea for it when he was 12 or something like that. And see, previously they'd invented television or, remote transmission of very rudimentary images, but it was all done mechanically. And what he did was came up with this idea was that you could scan things scan and paint basically with these tubes that shot beams of electrons. And if you think of scanning something, it's a raster process where you go left to right. Well, we go left to right. We assume we go left to right because that's the way we read. And we go down because that's the way we read. So that's the way these original scanning guns were set up for television. So they started at the upper left-hand corner and did just like we read. They went left to right, top to bottom. That is why we have our flash grid where the origin is at the upper left-hand corner. X gets bigger as we go to the right, which is the same as our graph, but what's different is y gets bigger as we go down. That allows us to position things on the grid starting at the upper left-hand corner and always be working with positive numbers, which is nice. But just get used to it that's the difference when we're talking about locating something on the stage, either in Flash or in Illustrator or in Photoshop. Most of the graphics programs and all graphic programming, I say all with an asterisk because I don't know quite enough to know assuredly that it's all graphics programming like coding, but everything I've seen all uses the origin at the upper left-hand corner. Okay, and it makes sense because if you were doing text or something like that, how does a text field expand as you add text to it? It expands to the right and it expands down. Okay, so we can blame Philo T. Farnsworth for this discrepancy. Boy, with a forehead like that, you'd be expected to invent television at 21, wouldn't you? And that name Farnsworth, remember Professor Farnsworth from Futurama? That's who he's named after. Actually, it's an homage to the inventor of electronic television. Okay, so let's go on and talk about graphing. So we are going to be graphing on an XY coordinate system, and it's different. And I want you to think about this. I want you to forget about your coordinate system in Flash for a little while, because this is not the same thing. We're not really locating things on the stage. What we're going to be doing is looking at rates of change. And that's what easing and tweening is all about. It's changing between two states, and you've got a rate of change. Okay, so for us, our x-axis is going to represent time. You know, these axes can represent anything. You know, it could represent, gummy bears per month or something like that. In this case, it's going to the x-axis will represent time, and typically we would express that in frames. So each one of these squares is maybe a frame. And our y-axis is going to represent change. Okay, I'm not talking about what kind of change. Could be change in position, could be change in color, change in alpha, change in rotation. Doesn't matter. What we're really going to do is abstract it to the point where we're looking solely at the proportion of time to change. Okay, so if we go on, one of the most simple graphs is this straight 45-degree angle, and you see that for every unit of time, we have 1 unit of change taking place. Anytime you see a straight line graph like this, what it is telling you is that there is no change in the rate of change. What kind of statement is that? Change in the rate of change. Change in the rate of change is speeding up or slowing down. And when you see a straight line, you know that there's no speeding up and no slowing down going on. Now, it could be a graph like this, in which case we're having less change per unit of time, but it's still a straight line, so there's still no change in the rate of change. It's going just as fast on the right-hand side of the graph as it is on the left. Okay? You could have a graph like this, and in this case, it's changing very much for a unit of time. Now, if we think of this in terms of a flash tween, I want you to think about the beginning keyframe of the tween as what's at the origin, and the ending keyframe of the tween, what's at the top of the graph, or in this case, at the right side of the graph. Okay? Now, I am talking about classic tweens here, which we were going to be dealing with almost exclusively, because classic tweens do give us more options as far as changing the rate of change. They give us more better ways to change our easing curves. Okay, so if you think about a tween like this, then that kind of tween is going to be, again, well, like I was saying, to belabor the point, straight lines mean no change in the rate of change. Let's move on. What about a change like this? I wish I knew who made this quote, who said this quote, and I could look it up, but I forgot to. Some mathematician has said that the greatest tragedy of the human race is our failure to understand the exponential function, which is kind of an interesting thing to think about when you think about things like population or things like that. And the exponential function is something where the rate of change starts doubling really fast. There's never mind. Okay, so if we look at this rate of change, looking at the origin, for every unit of time at the very left side of the graph, down near the origin, we've got very little change. But if we look at the right side of the graph, for every unit of time, there's a huge amount of change. I mean, look at this last unit there. That last column, you're going, maybe a third of the change is taking place in that last column of squares. That's the last unit of time. So, quick question. Answer to yourselves at home. Is this easing in or easing out? I've talked about speeding up on the highway. Easing in is speeding up on the highway. What about miles per hour? 5 miles per hour. That means you have 5 units of change per 1 hour per unit of time. 50 miles per hour means you have 50 units of change per hour. Okay, so what's going on here is this is easing in. We're going faster. As time goes on, our rate of change gets bigger. Okay, so anytime you see a graph like this, what this tells you abstractly is that the rate of change is increasing with time. If you see, I had the answer there all the time. I could have given it to you. I'm sorry, I don't have, I do actually have my slides listed out in front of me, but I don't have my glasses on because I'm looking out. Okay, how about this one? Easing out. Well, yeah, that's an easy one. Yeah, we've only got in or out. We're starting off, our first unit of time, we're doing probably a quarter of our change. Our last unit of time, we're just doing a little tiny bit of our change. You can also think about this as like riding your bicycle up a hill. Okay, let's go back to easing in. Okay, you start off at the bottom of the hill, and it's not very steep. You're not going up very much for every foot or yard or meter forward that you go. But by the end, you've thrown your bicycle. Actually, your bicycle has fallen down the ramp, and you are climbing. You're hoping for handholds. Okay, in this case, you start off climbing and with your bicycle on your back, and then when you get maybe up to the top, if you're careful, you can ride it. Okay, all your change in altitude has happened at the beginning. So yes, this is easing out. You're going from a high rate of change to a low rate of change. Now, the trick question. What in the world is that? That's a Landau bar. That's like they put on the old Thunderbirds. Now, this is actually called what is this graph called? I don't like the name of this graph. This is called a stop-start ease. But it kind of makes sense. In this one, at the very beginning, it's changing a lot. Then it quits changing so much in the middle. Then it starts changing a lot in the end. This one and the next one that we're going to look at, these actually are very, very useful easing graphs. Okay, so that's a stop and start. Stop doesn't necessarily have to be first or last or anything. It's just basically what somebody named them. Actually, these are all based on mathematical functions, and some mathematician called it this. I don't know what I'd call it. Landau bar, S-curve, whatever. Anytime that you see something like this, you can know that you've really got 3 different rates of change, then you're moving or transitioning smoothly between them. So here you're going fast, slow, fast again. In this one, and this is actually going to be one of our more common ones that we're going to use, we're actually going to demonstrate this in just a couple of minutes in the next part. But this is, again, an example of stop and start. In this one, we start slowly, then in the middle we speed up, and then we end slowly again. Think about this. Maybe I just watched this video on YouTube of this lamb that went with these two. It was New Zealand. These 2 guys took this lamb to the skateboard park, and they were on bikes, and the lamb was running up and down these things with them. But think about like skateboard park. Okay, you ride down, get into the bowl where you're going slower, and then, well, no, that doesn't work. Never mind. Don't think about the skateboard park. Okay, that would be more of one of the other ones where you slow down. Okay, so anyhow, this one, you start slow, go fast, end slow. Okay, so this is going to be the one that we demonstrate, and we will go on to that in the next part.